All right, hey AP Chemists, this is going to be the Unit 2 Important Information Part 1. We're going to be talking about the types of chemical bonds. So before we get there, I just want to introduce us to something called Lewis dot symbols. These are going to be a little bit of an illustration for the way that elements are bonding or how elements are going to be interacting. So Lewis dot symbols are assembled by using the atomic symbol and a series of dots placed around that symbol that indicate the number of valence electrons. Remember, sorry, there's a little typo there. Remember, the group number is equal to the number of valence electrons. So calcium. Calcium's in group 2. I would write its symbol as Ca, and I would do 1, 2 dots. That is the Lewis dot symbol for calcium. They represent the 2 valence electrons, and the valence electrons do all of the bonding. I have a nice little diagram over here on the side to show that at most we're going to see that elements will have 8 valence electrons for bonding and no more really. I'm going to skip down to phosphorus. Phosphorus is in group 5. So group 5 will have 5 valence electrons. So P1, 2, 3, 4, 5. I also wanted to do a little bit of review with looking at the electron configuration and seeing that the highest number electron orbitals or the highest number energy levels are the ones that will be found with the valence electrons. If I were to do calcium, notice how calcium has 2 valence electrons. It could form a positive 2 charge, which means it's going to lose those 2 valence electrons. So I'm going to draw that as just Ca2+. And the electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6. This would be the new electron configuration for calcium 2+. It lost 2 electrons from the 4s energy level. That's like review from our previous quiz. And in its outer shell now, in its new valence shell, it looks like it has 8 electrons. 2, 6, or 8. Something to note for later. I'll do the same thing for phosphorus. Phosphorus, it typically forms a -3 charge. It is going to gain 3 electrons. If I were to write its electron configuration, I would get 1s2, 2s2, 2p6. If we were to gain 3 electrons, it would be 3s2, 3p6. It's still in the 3rd energy level for valence, but look, it also looks like it now has 8 valence electrons in its new original valence. And I would draw that as P. Actually, I'll put the original dots in color so we have that. I would draw that as P, and I'll have the original 5 valence electrons, and then I'll add the 3 that it gained. 1, 2, 3, which this would have an overall charge of 3-. So just something to note about valence electrons and losing an original valence shell or even gaining electrons in the original valence. Just a note here, calcium lost its 4th energy level and it was left with its 3rd. The phosphorus had its 3rd energy level and it just added to it. Now, another thing to notice is, and I was pointing out that in these valence shells that there were 8 electrons here. 2 and 6 is 8. 2 and 6 is 8. Notice when an element reacts, an element becomes an ion, it becomes an ion, it has 8 valence electrons in its valence shell. It's going to be a very important number for us. This is known as the octet rule. This is going to be important for us for later. Elements tend to bond to fill their valence shells to this number. Calcium kind of lost 2, so it would have 8 in its new valence. Phosphorus gained 3, so it wouldn't have 8 in its valence. This idea of gaining and losing electrons, or even combining to have electrons that have 8 in its valence, helps us come up with a type of bonding. There are going to be 3 types of bonding to recognize, and I'm going to do that in these notes here. There's going to be ionic, covalent, and metallic, and I'll get to that in a moment. Before I could get to that, the reason why elements would have different types of bonds are because of their electronegativity. The type of bond is dependent on the electronegativity. So the type of bond is dependent on the electronegativity. To remind you, electronegativity is the attraction an element has for electrons. We have trends that were in our last set of notes. Fluorine is the most electronegative. I'm going to use En for electronegative. Francium, all the way down here, is the least electronegative. The closer you are to fluorine, the more electronegative you are. Closer to fluorine, more electronegative. That's a nice little trick for us. So the closer you are to fluorine, the more electronegative you'll be. And that is giving us our trend, or reminding us of our trend. Electronegativity increases as you go from left to right, so increases. It increases as you go from bottom to top. Increases in electronegativity. And if I were to ask you why, it would have to do with the effective. It would have to do with the attraction for valence electrons but with the nucleus. So the more protons in that nucleus, like fluorine, and the same kind of size or shells, the greater the attraction. As you go down a group, if you remember, francium is going to be quite large. There's going to be more shells. Electrons are going to be further away. That's a little bit of a reminder. So if I had these three elements here, if I had lithium, boron, and fluorine, and look at this, I drew their Lewis dot diagrams. Fluorine would be the most electronegative. Boron would be in the middle as far as its electronegativity, and then lithium would be the least electronegative. And if I was going to talk about boron and fluorine's attraction for this electron, lithium's like, meh, I don't want this electron. I don't care for this electron. So just like a little note. And boron could be like, ooh, I want it. I want it more than you. But fluorine's going to be like, no, I want it more. So that's what electronegativity means as far as elements, like the attraction elements have for electrons. Fluorine would rather have lithium's electron more than boron was, and that's because of effective nuclear charge and all that coulombic attractions there. I will just kind of end with this information here with saying that there are exceptions to the octet rule. Helium and hydrogen, and later on we'll see boron, they don't need octets. So I'll address that later. If you had to ask why, it might be for effective nuclear charge. It also has to do with the number of electrons in the valence shell. That'll be later. So this is Lewis dot symbols, electronegativity, and those valence electrons, and the attraction for the nucleus. Now let's talk about the three different types of bonds here to end. There are going to be three different types of bonds. There's going to be covalent bonds, ionic bonds, and metallic bonds. Here's our nice little tricks. Covalent bonds is when the electronegativity difference is kind of low middle, right? So kind of like non-metals-ish. That typically forms between non-metal and non-metal. Two non-metals. So when the electronegativity difference is kind of small, and we'll talk more about that in our next set of lectures, that's going to be telling us that we have covalent, or sometimes another word would be molecular bonding. Please write that in. Another word for covalent would be molecular bonding, just in case. Typical properties for molecular bonding is that it's low, so low melting point. They're usually gases or liquids with low melting points. They're insoluble in water. They are poor conductors of heat and electricity. I'm going to add in heat and heat. So low and poor. Their properties are weaker. So some examples would be like two nonmetals. So like, let's do NO2. We could do OF2. We could say something like a sugar, like C6H12O6. Those are all nonmetals. Even if we do two hydrocarbons, or a hydrocarbon, we'll call this a hydrocarbon. Just throwing that out here, C2H6. Also, Hofbrinkel. If you remember our diatomic elements, they are diatomic, so like H2, O2, F2, Br2, I2, N2, Cl2. Our diatomics are all covalent or molecularly bonded, so those are some good examples. And I also drew our example of two Lewis dot diagrams coming together. Covalent or molecular involves the sharing of electrons between low electronegativity atoms. So just a little note for us there. All right, so that is molecular bonding. Then we have ionic bonding. Typically forms between a metal and non-metal. We could also see polyatomic ions kind of sneak in there. Remember ion, right? So typical properties, those are going to be high melting points, solids at room temperature, conduct electricity in molten and aqueous solution. Molten means as a liquid, aqueous means AQ, that it's dissolved in water. This is the most important property for us. Ionic compounds do not conduct electricity as a solid. That's going to help us distinguish, ionic and metallic. And I'll get to that in a moment. Right? So ionic compounds do not conduct electricity as a solid. If I have table salt and I just have it as a solid and I try and see if it conducts electricity, it is not. They will have high densities and high boiling points. So high, solid, conduct, strong. Some examples, of course, would be things like sodium iodide, sodium chloride, potassium, let's say oxide. I'm just doing some random ones. Calcium oxide, just some ionic compounds. We're also going to see later, I'm going to have to explain something later, maybe anything with polyatomic, so like NH4Cl. This is polyatomics, but these are all nonmetals. But remember, polyatomic ions are ionic compounds. So just some examples there for us. And then finally, the last type of bond is metallic bonds. When the electronegativity difference is low, middle. I forgot to mention. Ionic bonds, the electronegativity difference is very high. When the electronegativity difference between all elements involved is very high, those electrons are going to be very combative far apart. We'll talk about that later. When that electronegativity is very high, we'll have ionic bonds. And then finally, metallic bonds, you could even really guess what that means. Typically forms between two metals. Okay, typical properties, high melting points, high boiling points, solid. Oh no, how am I going to compare this to ionic? Because it's very similar. Relatively high density, how am I going to compare this? This one right here. It conducts electricity as a solid. Metals or metallic bonding substances, they conduct electricity as a solid and molten. So that's nice and easy. But ionic substances do not conduct electricity as a solid, so remember that. And then, of course, some very simple examples for metallic. If I were to just say the element Fe, if I were to say the element just copper, I could even say like something like manganese and chromium. Just examples here, okay? I do want to say that the lecture is done here, and I just do want to make a note of some examples here. So to show your understanding of the types of bonding, I'd like you to do these practice examples and just identify compounds as ionic, covalent, or metallic, or both. I'm actually going to put the answer to both for two of them. This would be both. This would be both. I'm putting that in there for you so you don't have to worry about that. Polyatomic ions, compounds. Polyatomic ion compounds contain both covalent and molecular character. molecular, ionic. Why do we keep on saying that? Covalent and ionic character. Why? If you kind of look a little bit closer, like ammonium chloride is only nonmetals, right? NH4Cl. These are all nonmetals, but the bonding in NH4 alone is covalent, and the bonding between NH4 and Cl is ionic. And so if I look over here, I'm going to go back up here. Even though the notes are ending, I'm going to go over here. We're going to see that the bonding in NH4 alone is covalent bonding because you have N with 4 H's. Those are two nonmetals bound, but they overall give a charge of +1, and they interact and will interact ionically with Cl, which will have a charge of -1, and that is why overall this will be ionic. Between NH4 and Cl is ionic, but in the NH4 it's covalent. So the only thing I'd want you to know by the end of these notes right here for yourself is that polyatomic ionic compounds will have both covalent and ionic compounds. And be on the lookout for polyatomic ions, NH4+, OH-, C2H3O2-, just like famous ones here, sulfate. These are just famous polyatomic ions for us. Alrighty, that is the end of our notes. I'd like you to answer these sample problems by identifying the rest of the problems as either being ionic, covalent, or metallic.